Hi everybody. Today I want to talk to you about electric charge and Coulombs Law, and this lecture is to accompany section 3.7 in your Matter and Interactions textbook. So first, electric charge. As you probably heard, there's two kinds of electric charges, and we call that positive charge and negative charge. Positive charges are the kind typically carried by protons, okay? And then negative charges are the kind carried by electrons. Now, in ordinary matter, you have a nucleus with protons and neutrons in that nucleus, which is orbited by electrons, right? So neutrons are neutrally charged, and so that means that the nucleus of an atom, which is made up of protons and neutrons, has a net positive charge. And then the electrons are attracted to that positive nucleus, and so they orbit it, right? If you give something a tangential velocity but it's attracted to the thing, then it'll sit there and orbit it, just like planets do the sun, okay? Although, disclaimer, the orbits of electrons are better described by quantum mechanics because they're so tiny and we're very uncertain about their position, okay? All right, so what we know about charges is that the charges of the same sign, like negative to negative, for example, they're repelled from one another, whereas charges of opposite sign are attracted. Okay, so that helps explain the orbits of the electrons around the nucleus, like I was talking about earlier. Now, the Coulomb is the SI unit of charge, but 1 Coulomb is a ridiculously large amount of charge, okay? The charge on one proton, for example, is 1.602 times 10 to the minus 19 coulombs. So you can imagine that 1 coulomb of charge is a heck of a lot of protons. Now, the magnitudes of the charge on both the electron and the proton are the same, 1.602 times 10 to the minus 19 coulombs. But the electron has a negative amount of that charge, and the proton has a positive amount of that charge. And as I already said, neutrons are neutrally charged, so they have a net charge of 0. Now, we say that charge is quantized. What we mean by quantization is that it comes in little discrete packets. Since we've already talked about how much charge is on a proton or an electron, I bet you can guess the amount of the discrete packet. It would be 1.602 times 10 to the minus 19 coulombs, which we often call E, the fundamental unit of charge. So what that means is that any amount of charge that's larger than that would be equal to some integer number times E. So if you have, for example, a positive charge, then Q, which is what we often call the charge, would be equal to plus n times E. Whereas if you have a negative charge, it would be equal to minus n times E. Now, as I said, a coulomb is a really large unit, and the charge on the electron and the proton is a really tiny number. So that means that n is usually a really big number, okay? And of course it's an integer because it's not going to come in half packets. Electric charge is always conserved in isolated systems. You can't create or destroy charge except in packets or together. So what happens is, let's say that you have a balloon and you rub it on your head. What's going to happen is that that charge is transferred from one system to another by rubbing, okay? And so it's not created or destroyed, but it's transferred from one object to another. You can also transfer charge via currents and other methods, okay? Now, in modern physics, you learn that you can create particles out of nothing, right? E is equal to mc squared is the amount of energy that it takes to do that. But even so, charge is still going to be conserved. So, for example, if you've created a proton out of nothing, then you would also create an antiproton along with it. And so the net charge of the creation would still be 0 because you've got the proton, which is positively charged, and the antiproton, which is negatively charged. So you start with 0 charge and you end with 0 charge, okay? So you'll talk about that more in modern physics, so if that goes above your head, don't worry too much. So here in this little graphic, we talk about transfer of charges. So in this charge, what's happened, or in this picture, what's happening is that you have a glass rod and you're rubbing it with a piece of silk, okay? So what happens there is that when you rub the glass rod with the silk, charge is transferred from the glass rod to the silk. In other words, electrons are ripped off that glass rod and go into the silk, okay? This is called triboelectrification. Tribos means to rub. So you can blame today's lecture on this man right here, Charles Coulomb. He was a French physicist who lived and worked in mostly the 1700s. His major contributions were in the areas of electrostatics and magnetism, but he also investigated materials, structural mechanics, and ergonomics. So really busy guy. His experiment, which resulted in the law we now call Coulombs Law, is kind of similar to the Cavendish's experiment. Basically, he had some charged rods which were connected to one another via a light rod. So he had some charged balls on either end of a light rod, and the rod was attached to a fiber which was suspended from below. So if you put a net charge on those balls on the rod and then you bring another ball near it which is also charged, then that would cause a pivoting of the system, and then you can measure that pivot and hence determine the force. What he found was that the force depended upon the amount of charge that he put on the balls and also the distance in between the balls. Now I'm going to use the term point charge a lot here. What do I mean by that? Well, a point charge, a point particle, for example, is just something that has zero extent, okay? And a point charge is something that is zero in extent, so it's infinitely small in other words, but it has a net charge to it. Now, this does a really good job of modeling some systems like electrons, protons, nuclei, ions, and that's because these things are so small. So if you think about it, the spacing in between atoms in a solid lattice is on the order of 10 to the minus 10 meters or 0.1 nanometers, and the size of nuclei is on the order of femtometers, which is 10 to the minus 15 meters, so that's really teeny. So point particles, point charges, they model that pretty well. There's some other systems though, like if you have a macroscopic thing and you charge it up, maybe it's not as well modeled by the point charge model. So you really need to think about it before you just plug and chug into this thing, okay? Alright, now we're going to talk about Coulomb's Law. Let me go ahead and show you Coulomb's Law here. Here it is mathematically expressed. So this says that the force in between any two point particles, point charges, is equal to K, which is the Coulomb constant, 8.99 times 10 to the 9th Newton meters squared per Coulomb squared, right? K, times the product of the two charges in question, Q1 and Q2, divided by the center to center distance between those charges, R squared, right? And then times R hat. So the force is always along the line that connects the center to center of those 2 point charges, right? So that's what the R hat vector means. It means pointing from one center to the other center, okay? And then R is the center to center distance between those. Q1, Q2 are the charges of those things in coulombs. Don't forget to switch over to the SI units. Now, one more word about K. K is the Coulomb constant, but I can also, you might also see it expressed in the form of 1 over 4 pi epsilon naught. Epsilon naught is called the permittivity of free space, and the value of epsilon naught is 8.854 times 10 to the minus 12 Coulomb squared per Newton meter squared. Okay? So these two forms of Coulomb's law are seen interchangeably. Okay, so remember your charges have to be in coulombs, which means that you might have it written out in some scientific notation there. Okay? Typical charges, microcoulombs, nanocoulombs sometimes. So it's important, I think, for folks in the intermediate physics level and above to memorize those SI prefixes, okay? So go ahead and memorize the ones from about 10 to the minus 9 to 10 to the plus 9. Nano is 10 to the minus 9. Micro is 10 to the minus 3, okay? So those are some typical ones. But you should go through and memorize those SI prefixes. I'm not going to give them to you on tests, okay? You need to have those memorized. Alright, so let's take a look at the picture of these things. Remember that I said like charges repel and dissimilar signs of charges attract. Okay, so in this picture I have two positive point charges, right? And so they're going to be repelled from one another. Okay, so here what you see is a dashed line connecting the center to center of those 2 point charges. And you can see that the force vector for Coulomb's law points along that line. Now, because they're repelled from one another, it shows the two arrows indicating the forces pointing away from each other. So here, F21, which is the force on charge 1 from charge 2, that's pointing kind of down and to the left, away from charge 2, and then, the other one, F12, that's the force on charge 2 from charge 1, and that's pointing up and to the right, away from charge 1. R12 hat is the unit vector that points along those lines, okay? Now, this is the repulsive force, so that's the drawing for that. We also have the attractive force here indicated, so you have a positive charge and a negative charge here. So it's still along the line connecting the two charges, but now the force vectors are pointing in towards one another here, okay? So F21 points kind of up and to the right on that positive charge towards Q2, right? And then the force on charge 2 points down and to the left towards charge Q1. So this brings up a point, okay? If you have your Q1 and your Q2 and you're multiplying them times one another, let's say that you have two dissimilar charges right here. So I had Q1 times Q2. What I would end up with is a negative sign. The negative sign in forces usually just means attractive, okay? But as we'll see, that doesn't really necessarily have to do with the direction, except the direction along our hat. So there's some specific strategies that I'll lay out when I work the example problem for how to handle the sign in your Coulombs law. I'd also like to point out that electrical forces here, as you saw in those drawings, are obeying Newton's third law, which means that the force, for example, in the ones that I had earlier, charge 1 and charge 2, the force on charge 1 from charge 2 is equal in magnitude but opposite in sign from the force on charge 2 from charge 1. So looking there, you can see that these vectors are the same length, which means they're the same magnitude, but they point in opposite directions toward one another, in other words. Now, the sign of the product of Q1 and Q2 gives the relative direction of the force between Q1 and Q2. If you've got a negative sign there for Q1 and Q2 when you multiply them together, that means it's attractive. If you've got a positive sign when you multiply Q1 and Q2, then that means that it's repulsive. But the absolute direction of your vector is determined by the actual location of the charges. So what I encourage you to do is to draw yourself a picture whenever you have to work with one of these questions. Draw the arrows in question showing which direction the force is, and then determine the sign on the forces from there, from your picture. Also understand that it obeys what's called the superposition principle. So if you have a collection of charges, say that you don't just have 2, but maybe you have 4 charges, like shown here, then the total net force on charge 1 would be the sum of the forces from each one of the charges. So let's say the force from charge 2 on charge 1 plus the force from charge 3 on charge 1 plus the force from charge 4 on charge 1. You'd have to do a vector sum of all those forces to get the net force on charge 1. That's what the superposition principle is basically saying. So pictured here, let's say that you want to know what the net force is on charge 3 from charges 1 and charge 2. What you'd have to do is you would have to first draw yourself a picture with arrows included to show the direction of the force vectors from charge 1 and charge 2 on charge 3. So here on charge 3, you have a positive charge 3, and it would be attracted to that negative charge 2. So I go ahead and draw the attractive force on charge 3 from charge 2, which would point to the left here. Then I would also draw the repulsive force between the positive charge Q1 and the positive charge Q3. It would be along the line center to center connecting, but away from charge 1, so that would point up and to the right. And then what I would have to do is I would have to solve for the components of F13 and F23, and then do the vector addition of those two things in order to solve the problem. Let me do an example problem for you. Here we have an arrangement in an equilateral triangle of 3 charges. There's a +2 microcoulomb charge at the origin, there's a 7 microcoulomb charge at the top of the triangle, and there's a -4 microcoulomb charge bottom right on the triangle. The equilateral triangle, of course, has interior angles of 60 degrees by definition, and each one of its sides is 0.5 meters in length. So for this configuration, what they want you to do in this question is to find the force on that negative charge at the bottom right. So what's the net force on that -4 microcoulomb charge? So there's a certain set of strategies that I solve each time I have to solve one of these problems. Okay? So here's my strategy. First I draw a picture, and on that picture I pick an origin and I label all of the forces from all of the charges on that. I draw them as arrows. And I would label any angles that I have there with respect to my x, y, and z axes maybe on that picture. Next step, I find the magnitudes of all the forces that are in my picture. Next step, I find the components of those force vectors using trigonometry. And then finally, I perform vector addition of the forces. So those are the steps that I follow each time I have to do one of these problems. So let me now apply those steps to this problem. Step 1, draw the force vectors. Okay, so I'm trying to find the force on this minus 4 microcoulomb charge at the bottom right of my triangle right here. So there's going to be an attractive force on this minus 4 microcoulomb charge due to the positive 2 microcoulomb charge at the origin. So I draw a force vector along the line connecting those two charges, right? And it's going to point from the negative charge to the positive charge. So that's this arrow here, which I've labeled F2, okay? Next, there's going to be an attractive force between the negative charge at the bottom right and the positive charge up here at the top of the triangle, okay? So I've labeled that F7, and I've drawn it along the line connecting those two, right, center to center, from the negative charge towards the positive charge. I made that arrow longer because the 2 microcoulomb charge over here is smaller than the 7 microcoulomb charge up top, so that would result in a larger force vector. It's not necessarily to scale, but it does help me keep things in my head. Okay, so that's step 1. Now the angles are already kind of labeled for me because all the interior angles are 60 degrees. Okay, so they were already labeled in my picture, so I didn't need to do that step. The next step is to solve for the magnitude of the forces that I just labeled. So F7, applying Coulombs Law, would be K Q1 or Q4 times Q7 divided by the distance between them squared. Okay, so that's the magnitude. So here I have F7 magnitude is equal to 8.99 times 10 to the 9th in SI units times the product of the magnitudes of those two charges, 7 times 10 to the minus 6 times 4 times 10 to the minus 6, right, because micro is 10 to the minus 6, and then divide by the center-to-center distance between those charges, which is 0.5 meters squared. Now when I solve for that magnitude, I get 1 Newton, okay? Now you might have said, hey Dr. Coffey, when you did that, you didn't plug in the sign of the charges. You didn't say that it was plus 7 times 10 to the minus 6 times minus 4 times 10 to the minus 6. Okay, but I just want the magnitude of that force vector. See, when I drew the force vector right here, I already indicated its direction, so I already indicated that it was attracted to that force vector. So don't double dip on your signs. You're going to go ahead and resolve those forces into vector components down here, right? All that minus sign or plus sign in the force does is tell you whether it's an attractive force or not, but I've already labeled it down here, so don't double dip, okay? Next, I found the force, the magnitude of force 2, which I've labeled F2 here, which is the force in between the minus 4 microcoulomb and the 2 microcoulomb charge. So, following the same kind of idea that I did on F7, its magnitude is 8.99 times 10 to the 9th in SI units times the magnitudes of the charges, 2 times 10 to the minus 6 coulombs times 4 times 10 to the minus 6 coulombs, divided by the distance center to center between those charges, which is half a meter, and then squared. So when I solve for that magnitude, I get 0.29 newtons, okay? So that's my next step. My next step says, okay, to break the forces into their vector components, okay? So F7 here, well, let's do F2 first because it's easy. F2 does not have an x component, or it does not have a y component. It lies entirely along that x-axis, and it points in the negative x direction. So I can go ahead and write F2. F2 would be equal to the magnitude of F2 in the minus I hat direction. So I've written F2 is equal to magnitude of F2 times minus I hat. Okay. Now let's do F7. It's harder. All right, so F7, that interior angle of the right-hand side of that triangle right there, that's 60 degrees. Now I've shown that, I've broken down F7 independently in a little drawing here on the bottom right. I've drawn F7 pointing up and to the left. That angle right there is labeled as 60. Now I need the x and the y components of that triangle that the vector makes, okay? So since this is 60 degrees right here, the x component is adjacent to the 60-degree angle right there. So that means I'm going to use cosine. And it points in the negative x direction, so it's minus cosine of 60 I hat. Okay? Now the y component there, it points up, so it's positive. And if I use cosine for the x, I use sine for the y. So f7 is equal to the magnitude of f7 times minus cosine 60 I hat plus sine 60 j hat. Everything is in degrees, of course. Okay? Alright, so that's how I find my components. Now what I'm going to do is I'm going to take that magnitude that I saw for the 1 Newton and the 0.29 newtons, I'm going to plug and chug it into these formulae that I have for F7 and F2 on the next slide. So finishing it off, F7 is going to be 1 Newton times minus cosine 60 I hat plus sine 60 j hat. When I multiply those through, I get minus 0.5 newtons in the I hat plus 0.87 newtons in the j hat. Okay? Now F2 was 0.29 newtons and it points in the negative I hat direction, so F2 was minus 0.2 newtons in the I hat direction. Now I'm going to perform vector addition. Remember, that's component-wise addition. So you add the x components to x components, you add y components to y components. Never, ever, ever add x and y components together. Okay, don't do that. You add them component-wise. X to x, y to y, z to z. So this is a 2D problem though, so I end up with F2 plus F7 would be minus 0.5 newtons plus minus 0.29 newtons in the I hat, which gives me minus 0.79 newtons. And then in the j hat, there is no j hat component to F2, so I just end up with plus 0.87 newtons in the j hat. Okay, so that's the net force on that 4 microcoulomb charge. And that's the same strategy that you'll follow for all of them. It may be more complex, you may have more charges, but that just means that you add on more forces. Let's take just a second to compare the two force laws that we've learned about so far, okay? We have the gravitational force, right? Newton's law of universal gravitation, and we have Coulomb's law. Now you might have noticed that both of these are inverse square laws. In other words, you've got some stuff, right? And you divide by the square of the distance between those two things. So these laws look super similar. I have F is equal to K, Q1, Q2 over R squared R hat for Coulomb's law, and I have F is equal to minus G, M1, M2 over R squared times R hat for Newton's law of universal gravitation. These things have very super similar forms, okay? Now, let's compare the magnitudes of these two forces, because that's worth a think too, okay? Remember, Coulomb's constant is 8.99 times 10 to the 9th. That's a pretty big number. Whereas the gravitational constant, big G, is 6.673 times 10 to the minus 11, which is a pretty small number in SI units, okay? So, big number, small number, right? It's no wonder that the gravitational force is so much smaller than the Coulomb force. Let's compare it for a proton and an electron in the Bohr model of the hydrogen atom, okay? So the Bohr model of the hydrogen atom puts forward that the proton is the center and that the electron encircles that in an orbit. Now in the ground state orbit, the distance in between the proton and the electron is 5.3 times 10 to the minus 11 meters. It's super tiny, okay? So let's plug into Coulomb's law there and figure out what the net force is on that electron from the proton. So 8.99 times 10 to the 9th times magnitude, 1.602 times 10 to the minus 19 coulombs squared, because both the proton and the electron have the same magnitude of charge, and then divided by 5.3 times 10 to the minus 11 meters squared. That gives a magnitude of the Coulomb force of 8.2 times 10 to the minus 8 newtons. Alright, now let's compare the gravitational force between the proton and the electron there. So here we're going to have the mass of the electron is 9.11 times 10 to the minus 31 kilograms. It's teeny. The mass of the proton is 1.67 times 10 to the minus 27 kilograms. Also teeny. Now, the distance in between, we already said 5.3 times 10 to the minus 11 meters. So we get, for the magnitude of that force, 6.673 times 10 to the minus 11 times 9.11 times 10 to the minus 31 times 1.67 times 10 to the minus 27 divided by 5.3 times 10 to the minus 11 squared. When you do that, you get a super, super tiny force 3.61 times 10 to the minus 47 newtons. Okay? Teeny. But compare it to the Coulomb force. Originally we looked at that and thought, oh well, that's not a really big number, right? 82 nanonewtons doesn't sound like a lot, but it sounds huge compared to 3.61 times 10 to the minus 47 newtons. So if you were to take the ratio of these two forces, 8.2 times 10 to the minus 8 newtons divided by 3.61 times 10 to the minus 47 newtons, you'd get a whopping 2.3 times 10 to the 39. So that's the ratio of those forces. There are 39 orders of magnitude apart. Okay? Now, the form of these forces is very similar. Both gravity and electromagnetic forces are inverse square laws, and they both theoretically have an infinite range. Okay? But gravity is the weakest force of all the fundamental forces of nature. Remember, there's four: electromagnetic, gravity, weak force, and strong force. Those are the four fundamental forces of nature. Gravity is by far the weakest of all those forces. But remember that the weakest of all the forces actually dominates the structure of the universe, right? If you think about what happens in galaxies, they're all circling around. It's gravity that's driving the day in terms of that. So why, if the electromagnetic force is so much stronger, does gravity dominate? Well, think about it this way. The electromagnetic force is very strong, right, compared to gravity. But what would that mean? That would mean that charged entities, right, are going to be moved together, and then eventually they're neutrally charged. Okay? Well, once they're neutrally charged, what happens? There's no more Coulomb force anymore, right? Because you've got to have a charge. But you've always got a mass. Okay? So even though gravity is a weak force, the mass is always there and it's working for you, and so it dominates the structure of the universe for that reason. All right. I'm going to sign off there for today. If you have any questions, let me know, and as always, see you in class.